All right, this is the first podcast of Unit 7, and we are going to be talking about chemical reaction types on pages 5 and 6 in your packet. I know we just barely started this packet. We might have only finished page 1, maybe not even started on page 2. You might have started a little bit on pages 3 and 4, maybe not at all. We will come back to pages 2, 3, and 4 in class next time, but we are going to add in these reaction types in addition to the balancing. So page 5 is where we're going to start. And the first thing I want to talk to you about is actually not written on page 5, but all of these chemical reaction types are going to come back to looking at the types of substances that are on either side of the arrow in a chemical reaction. We've got to be able to look at them and tell if they're an element or a compound in order to be able to do most of these types. And if you remember from back in Unit 4, compounds are what we make when we put two different elements together. So like NaCl, MgCl2. And an element is just one type of atom, one symbol only. And it doesn't matter whether it has an extra number on there, like Cl2, that's just chlorine. It's a diatomic element, but it's just one symbol, so it is still an element. So we got to remember that. You might make a little note of this in the margins if that's not something that's automatic to you. And we're going to look at each of these types as kind of a chunk. And so you can see here, this is the synthesis chunk. And synthesis is one of our 5 types of reactions. Sometimes it's called the combination reaction, so you might write that down there. One of the other things I have here in this space to help you understand a synthesis reaction before we even write down this always statement that we're going to make sure to get for every reaction is this is what we call a generic equation. These aren't necessarily elements. There is no element A or X. But I'm using these as just simple letters to show you how the kind of pattern that happens in a synthesis reaction, because that's what these types of reactions are going to be, is some patterns, some similar types of reactions that have similar patterns in what the elements do, how they move and change. So this synthesis reaction, as you see here, A and X are separate before the arrow, and they're coming together to synthesize AX. They're combining, that word combination there, to make AX. And all synthesis reactions only have one product. And that product here is the AX. And that is a compound. So if you're looking for a synthesis reaction, you're going to look for a reaction that just has one compound after the arrow specifically. And you can see that that one product, that compound in the 3 examples below, you can see Mg plus O2 is making MgO. Seeing that one product means this is a synthesis reaction. And even in a word equation, even when we see lithium oxide, because we can tell that's a single compound, because that oxide tells us that it's together with the lithium, not just lithium and oxygen, then that's also synthesis. So you don't necessarily have to write and balance an equation to tell it's synthesis. Just look at the pattern. We've got 2 things coming together to be one. That's synthesis. Now, sometimes it could be 3 things coming together to be 1 or 4 things. It doesn't even matter whether they're elements or compounds, as long as whatever reactants you have, whatever stuff you have before the arrow, comes together to make one single product. Okay? So we're going to go through the other 4 types of reaction in the same way. Make sure to get the always statement written down, as well as make sure you're looking at that generic equation that I highlight and seeing how that relates to that always statement. Now, the thing that you may or may not choose to write down is what I have here in pink. Sometimes it helps people to have an analogy to relate to these reaction types. And so I think it helps sometimes to help us remember some of these patterns, especially when they get more complicated. But this one is a simple, happy analogy. It's a marriage. A and X were starting separate. They got married. They got together, formed a compound, formed a married couple. So if you're thinking about synthesis and you think synthesis is the marriage, you can kind of remember that pattern of how they come together. Now, decomposition is very similar to synthesis, but it's kind of the opposite if you look at that generic equation. AX is becoming A plus X. They're separating. So, not such a happy analogy, but I do sometimes call this one the divorce. Decide whether or not to write down that pink part, whether it helps you remember it or not, up to you. But what you're always going to see for a decomposition reaction, what you got to make sure to write down, is that these only have one reactant. And that reactant is always going to be a compound, something like that AX, more than one element together. And you can see in all of these examples here, there's one compound before the arrow, only one substance before the arrow, more than one substance after it. Now, in all of these examples, you see that we also have this heat or electrical current written out. You're almost never going to actually see us write that out, though. But all of these reactions do tend to require some amount of energy. Even the ones that could happen at room temperature wouldn't happen in the freezer. They need that room temperature heat to be able to react. So, decomposition, opposite of synthesis. Single replacement. You actually have two different generic formulas here, generic equations to look at. Because there are actually two different types, two different flavors of this single replacement reaction. But one way or the other, each of these reactions are single replacement, and each of them has an element and a compound on each side of the arrow. And I know all of these, I color-coded my elements all green, my compounds all blue, and that was when I noticed that on each of them it went element, compound, compound, element, compound, compound, element. Now, that's not always the case. Here we could have written this out, Ag2SO4 plus Cu. The stuff on either side of the reaction can go in either order. It could be compound plus element makes element plus compound. It doesn't really matter, as long as each side of that arrow has one element and one compound. That's the key. And no matter what, if you want something to be single replacement. Now, in each situation, here we do have an element plus a compound. And just like I mentioned before when we were talking about elements versus compounds before we got into these notes, these diatomics like Cl2 do still count as an element. So that is an element. KBr, two different elements, that's a compound. And that's really the only big difference between these two types. We're going to get more into metals replacing metals, halogens replacing other halogens. But when it comes down to it, this is what I call the homewrecker reaction. It's not a happy analogy, but it's a very memorable one, which is why I use it. And I think that the metal one is a little bit simpler to see this happen with. Our A is single, BX is a nice, happy compound, or so they thought until A came into the picture. And that's when X decided they would rather be with A than B. And so X broke up with B and ends up getting with A, and now we've got single B left over afterwards. So X is making a change and reacting to form a new compound. So like we said in that always statement, we have an element and a compound on each side, but it's a different element before the reaction and after the reaction. It's a different compound before the reaction and after the reaction, because that compound has switched part of it out, but just one part of it has switched. The part that stayed in the compound decided to kind of trade up to the better partner. And the same thing is happening with that second set of examples. The only difference, since these are halogens, those are all diatomics. So you're seeing that Y2 plus BX. And when that Y is reacting with BX, because the halogen part is the negative part, the Y is replacing the X here. So overall, like what it was just showing up here, what happens, metals replace metals because they have the same type of charge. Positives replace positives. Halogens are both negative. Halogens replace other halogens. Basically, negative stuff replaces negative stuff. Now, we're going to get way more involved with that later on when we're predicting products. But we've got an element replacing part of a compound, leaving someone new single as their own separate element with a new compound there. Now, double replacement is our last and biggest type. And you can see by this generic equation already that there's a lot of compounds in here. In fact, In order to be a double replacement reaction, you have to have two compounds on each side of the chemical equation. And that's really it. This is the only type of reaction that's going to be compound plus compound, making a compound and a compound. Now, just like in single replacement, oh, where's my note? There we go. Just like with single replacement, the elements with the same charge are going to replace each other. And this is going to be more important once we start predicting products. But if you notice, this pattern is actually really important. The A and the B are going to be switching places here. So they're swapping out with each other to make two new compounds. But each of them still has an A and a B, a X and a Y. It's just now A is with Y and B is with X, where A started with X and B started with Y. And that's why I call this the wife swap. And don't get too many crazy ideas about this. This was an old TV show that's probably before your time, but it was kind of funny. They took the mom or the wife out of whichever couple, out of two different couples, and swapped them and let drama ensue, because of course they would take this nice straight-lined vegan, very clean and organized mom and put her in this house that had no organization, that ate meat all the time, and expected her to cook and clean for this new different household. And then they took that really sloppy mom and put her in the really neat household. And like I said, shenanigans ensue. Lots of drama. Great TV show for its time. But that's what's happening here. We're taking the positively charged thing out of each of them and swapping them and seeing what new stuff we make, what new drama, what new compounds we can make here. Now, a lot of these blue notes that I've made here are extra stuff that we'll come back to in more detail later. But while we're talking about these things, you can already kind of see it. So I wanted to make that, kind of point them out to you. And our last type is a combustion reaction. And this one, honestly, there's no real analogy for. I tried to come up with an analogy once upon a time, but it got even messier than that home wrecker reaction. So we're not going to go there. But combustion reactions are just burning stuff. Every combustion reaction involves burning, even though not everything that burns is a true combustion reaction. Because in order to be a combustion reaction, as you see in that generic equation, it's not very generic. There's some real elements and compounds in there. In fact, every single combustion reaction will always have the same key parts. Sorry, I had to move that highlight pink area over. That O2, CO2, and H2O part are always going to be exactly the same in every single combustion reaction. The only part of a combustion reaction that changes is the hydrocarbon. So here where I wrote CX and HY, because hydrocarbons are just carbon and hydrogen together, I have an X and a Y down here. Those X's and Y's could be different numbers, like 3 and 8, 2 and 6, 2 and 4, 1 and 4, like all different numbers. Those numbers might change, like what you see down here, but they are never going to be different, crazy, extra stuff on either side. So it's always going to be some kind of CH thing plus O2, not O3, not just O, always plus O2, and then the arrow. There will never be any extra chemicals or substances there. And the great thing is that it always makes CO2 and H2O. The only thing that might change about it, and I didn't give you any good examples of this down below, is that sometimes the order changes. So like this H2O and CO2 could be in a different order. It doesn't really matter as long as they're both products of the reaction. And for that matter, we could switch the hydrocarbon and the oxygen. Most of the time it's going to be hydrocarbon plus oxygen, but it could be oxygen plus hydrocarbon. So it doesn't really matter the order, as long as both of those things are reactants, both of those things are products. So you've got a nice little summary down there at the bottom of the page, which could be a nice one-stop shop to look at. If there are any of those notes that I wrote in those bigger areas of our notes, you could transfer them over here, but that's kind of what I kind of imagined the more in-depth notes taken on pages 5 and 6 kind of in long form, and then this can be your one-stop shop if you're trying to classify something. I got the generic equation here and kind of the always statement that you needed but not as much detail into how and why and what's going on with each of them. So, hope that wasn't too painful.